Yes, good morning. I'm Mr. Orkodip Mondol, Assistant Professor of Electrical and Electronics Engineering Department of Regent Education and Research Foundation Group of Institution. Dr. Debangshu Dey, Associate Professor of Electrical Engineering Department, Jadavpur University. I'd also like to welcome our research chair and all the faculties and all the students present over here. Today, I am glad to inform you that Dr. Dey is present with us for delivering his speech, Synergism of Machine Learning and Signal Processing for Condition Monitoring Applications. Dr. Debangshu Dey is working as an associate professor in the Electrical Engineering Department, Jadavpur University, Kolkata, India. Dr. Dey has published more than 125 research papers in international journals and conferences in the fields of his research, including 28 papers in IEEE transaction and co-authored two books from Springer Verlag, London. And Elsevier also edited two volumes published by IEEE. He is the principal investigator of 3 government-funded projects. 6 patents have been granted to him, of which one is a he is the recipient of IEI Young Engineer Award in 2014. He is the recipient of IEI Young Engineer Award in 2014, Air Research Excellence Fellowship from ACRB, Government of India, Vishveshwara Young Faculty Institute like University of Applied Science, Augsburg, Germany, and ISI Kolkata, and also the member of Committee ETD 53 of Bureau of Indian Standards. His name is included in the list of top 2 percentile researchers worldwide published by Stanford University and Elsevier VV. His areas of interest are applications of signal and image conditioning and processing tools in electrical and biomedical.
It is very minute of signal processing to these AI/ML tools, then they can perform splendidly well. That means their performance can be increased manifold. So that is the idea. We are trying to discuss that particular thing. That means how we can mix up this or mix these signal processing tools and machine learning tools to achieve something that higher performance level, which is otherwise not possible and decision support. So crudely speaking, this data acquisition, that is some sort of you must have some hardware data acquisition setup that will acquire the data, and denoising and other things where we can use some signal processing. But the analysis and decision support, most of the cases they are solely governed by some AI/ML tool. It can be a classifier, it can be a regressor, or whatever according to our problem. This tool we can choose. Now, let us have one specific example. Today we are going to discuss one of my examples will be a partial discharge. Partial discharge, those who know that is fine, but maybe it is an interdisciplinary audience, so that's why I'm explaining partial discharge a bit. Partial discharge means it is in electrical or any electronic circuit, there will be some insulation. Mostly for electrical insulation, those insulation may have some defects during manufacturing. For example, that insulation may have some void in it. If there exists some void, if there exists some say defect within that particular insulation, what will happen? Gradually we'll be using that insulation with say high voltage or a voltage level that is supposed to exert across that insulation. But that because of that void, what will happen? It will not break down completely. But in that void, local discharge will occur. That means local sort of say some ion discharge will occur. And that discharge, if we go on, if we allow it to persist, then what will happen? These images will show you. That is, from that particular void, gradually that particular insulation will degrade. Gradually the insulation will become very poor and very weak, and eventually the dead short circuit or a fault may occur. The point is, if we can identify this kind of a partial discharge earlier, or if we can predict what is the location, then we can take a preventive measure. So that preventive measure will be very useful for this kind of an action or reliability of use of various systems. Now, this is one kind of data acquisition setup for that we can use for partial discharge, and this kind of a setup we can use in laboratory as well as most of the cases in laboratory. And this is a sample. It can be the sample actually just showing one insulation and using one void. But it can be this particular thing, this sample can be a transformer. So the transformer insulation will be the insulation we are investigating, and the void within that transformer insulation could be our source of partial discharge. So whenever we record the signals looks like this. So whenever we record the signal will look like this one. You can see that those signals are very noisy because the partial discharge signals, whatever we get, that is in the order of microvolt, millivolt, because the charge discharge, the amount of charge is of the order of say nanocoulomb, picocoulomb, like that. So therefore, their external effect, that means the signal they will generate, will be of very low magnitude. So whenever we record them, noises are also in that amplitude range, as well as some portion overlaps with the frequency domain also. So therefore, whenever we record the partial discharge signal, we invariably record some amount of noise as well that is visible here. So later on, we'll see that this portion, if we follow my cursor, this portion is having some higher magnitude. So we can say, apart from noise, there is something else. Similarly, here also, we can see that the amplitude is somewhat more than the average amplitude of other portions. So something is happening here. So usually we prefer to look into this in terms of or with respect to our power frequency signal. Probably you know our power frequency signal is 50 hertz signal because all of our supply voltages, they are having a 50 hertz frequency AC. So therefore the whole time period is 20 milliseconds. So with this sinusoidal waveform, if we superpose this partial discharge with sinusoidal waveform, the waveform looks like this right side of image. That means this is a sinusoidal waveform and superposed with the noise plus partial discharge. So what is our problem? Our problem in hand is what we are trying to do here is we are trying to find out the partial discharge signals. We are trying to identify that whether there exists any partial discharge signal or not, because we may have a misconception that we can see the noise and we can feel that okay, the noise is actually the partial discharge, or vice versa, there exists a partial discharge, but we can discard that as a noise. So this is the problem. So we have to identify the partial discharge and what kind of partial discharge is it, what kind, I am just explaining it later on. But now we have to do something with the signal that we have recorded. And condition monitoring, I told you, the initial part is data acquisition, and the second part of condition monitoring is with the data we have to do some analysis. Again, that analysis we can look into it into two ways. One, we call it a feature extraction, and the second one we call it a classification. So one part is feature extraction and another part is classification for condition monitoring problem. So here we are having the data. So you have to do something. We have to do something that we can extract certain signature from the signal that will tell us whether there exists a partial discharge or not. So just extracting those signatures, proper indications from the signal is called the feature extraction. And classification means we have to classify whether it is a say, for example, if it is a binary classification, we can have yes, no. That means yes means there exists a partial discharge. No means there exists no partial discharge. Also, it can be a multi-class. That means if it is a partial discharge, what is the location? If it is location 1, it is class 1. Location 2, class 2, like that. So in various ways, we can frame our problem according to our requirement. Now, it is always preferred in case of this partial discharge because the signal is very low. It is more prone to noise contamination. So the noise-free signal is always preferred. Now, feature extraction, here we will just discuss that we can have this. We can do the feature extraction with cross wavelet transform. But whatever we use, we must answer the one question, that is the why. Why should we choose cross-wavelet transform? We will explain that later on. But what is wavelet transform? Let us first discuss that. Maybe many of you just know this, what is wavelet transform. But again, I am repeating for continuity of the or flow of this lecture. I will explain this a bit. Maybe this audience is mixed or interdisciplinary. Maybe some of you know whether what is wavelet transform. Maybe some of you doesn't know. But I'll try to have an overview of that. We know that using Fourier transform, we can have that frequency component of a signal. Now, if we are trying to find the frequency component with respect to time, that means at which time, what kind of frequencies they are present in a signal. So in that case, it is called a time frequency representation. Wavelet transform is quite well in representing a signal in time frequency plane. And in say, for example, this is a top waveform. This top waveform is called sometimes called a chart waveform. Chart waveform means its frequency is not constant; it is varying. Varying means initially the frequency is low, and gradually, if we move towards right along time axis, x-axis is the time axis. So if we move along the time axis, the frequency actually becoming low. So if we perform the wavelet transform, whatever may be the equation, the mathematical equation is not important here. If we perform some mathematical equation like that we do for the Fourier transform, like that if we similarly if we perform the wavelet transform on this waveform, the plot will look like this. We will be having a two-dimensional plot. One axis will show us the frequency. Here in terms of your frequency is called scale. Scale is inverse of frequency, and another axis is time. And this particular, all those values will show you that at which time what kind of frequency will be there. Low scale means high frequency. So initially high frequency means you can see here the peak region means coefficient will be high for that particular frequency. So at lower time, that is from 0 to 50, the peak is belonging to low scale. Low scale means high frequency. So as we move on towards the time axis, along if we move on towards say 200 time units, it can be second, it can be something, okay, the 200 time units, the peak moves towards higher scale. Higher scale means in wavelet transform it is low frequency. So in this way, the basic idea is that if we perform wavelet transform, we can find the time frequency localization of a signal. That means at which time what kind of frequencies are present in a signal. Now, cross wavelet transform is actually compares the wavelet transform of two waves. That means we are having two waveforms, x and y. So if we compare the trying to find out the correlation between two wavelet transforms of the wavelet transform of x and y, then what we'll get? We'll get the time frequency similarity or time frequency correlation between two signals. That means at which regions two signals are having similar features or similar properties. They are quite helpful in identifying partial discharge. Why this kind of feature is helpful, I'll explain. But my point is that whatever tool we may use, whatever signal processing or any other tool we use, there must be some purpose. That means some problem that it should solve. According to that, it is not that there are n number of tools. Any one I can choose. So I am choosing them randomly. It is not that. So depending upon the problem, we have to properly choose the signal processing as well as machine learning tool. Then only we can have the exact or the desired level of performance. Why we are choosing the cross wavelet? Let us discuss that one. So here, what we have done, it is a noisy PD pulse. The initial, if we follow my cursor, it is a noisy PD one. And the right one is the power frequency reference. It is a sinusoidal 50 Hz signal that usually we apply. And if we just add them, so this is my signal. And if we perform this signal, that means follow my cursor, this is the signal. And this is the noisy PD. If we perform cross wavelet of these two, that means we are comparing this one with that one. If we are performing the relationship of these two, so the cross wavelet spectrum that will look like this one. So this is the image, and let us have the clearer view of this. It is this. So this image actually gives the color code, means red color means higher value. That means where the red color or yellow color, those regions gives you the idea that in those regions two signals are similar. Two signals are giving similar properties. And the blue regions, they are having lower value, that means mismatch. That means on those regions two signals are not so similar. So here in this image we can find that there are two regions, there is something on blue background, there is something is happening. That means some similarity is there here and there. If we follow the cursor here, one place and another this place. So why it is like that? Let us understand the partial discharge. That's why we are comparing in this way. See, partial discharge, if it is a power frequency signal, partial discharge occurs nearly to the where your field is high. So therefore, in these regions, near the peak region, sometimes there are different kinds of partial discharge. What I am showing you here, it is showing this region. That means here near the say one peak, approximately near the peak region of the sinusoid, and on the negative half cycle as well. So this is one, the right side image is actually one cycle, one particular cycle is shown, and we have taken the real life data using the LabVIEW software, using the data acquisition software and hardware as well. So this thing tells us that partial noise may be present all over the 50, say all over the 20 millisecond, all over the cycle. But partial discharge occurs only at some regions. So whenever we just correlate two waveforms where they are having some similarity is this region. And noises, and most of the cases they are uncorrelated, so therefore they will be not be giving some indication here. Only the partial discharge, they are occurring at the two half cycles, that is there in this image that is showing. So that is the purpose that we place our signal processing tool in that way. So that is the philosophy behind this. Now with this, with the diagram, we can of the particular waveform, we can extract some statistical measure like that. We can have that says what is the CG, what are the local peak locations at which time, which frequency. So in this way we can find out some fruitful features. So these are the features I have taken. Maybe in your problem your feature could be something else, some different equations you can choose. And these are the scatter plot. We have taken 4 classes here. I told you the classification may be your binary classification, or the classification can be say multi-class. Here we have taken the multi-class classification. So D1, D2, D3, D4, they are the 4 classes. What are they? Let us discuss that. These 4 classes are D1, D2, D3, D4. D1 is a narrow void. I'm just keeping this thing simple. That's why only 4 classes. More complex problem will have more other things, more other classes as well. So here it is D1, D2, D3, D4, and it is D1 is narrow void in contact with the electrode. D2 is the narrow void away from the electrode, and D3, D4 are the large void and in contact and other. That means we are trying to locate what is the location of that particular partial discharge. If we can locate, we can take a measure to change the insulation of that position, change the insulation of that location of that instrument, so that the partial discharge cannot lead to a deadly fault. So feature extraction part is over, and that feature extraction shows that the classes they're overlapped. So manual screening we cannot segregate them. So some feature extraction, some classification tool we should use. So the classical way of doing thing is that we have a feature extraction, that is a signal processing tool, and the classification is AIML. This is the classical one. So and we have used, in our case it is rough set theory we have used because of some reasons. That is why we have used rough set theory. Maybe in your problem you can choose any other classifier tool that fits the problem. Why the rough set? Because whenever we choose the features, we do not know whether those features are fruitful or not. Maybe we have chosen two features having more or less same information, or we can have so many features. Maybe we have chosen 100 features, or actually the problem could be classified with only say 50 features. Who knows? So initially, most of the cases we do not have any idea that what is the number of efficient features that we should choose, what are the number of optimal features that we should choose, or whether a feature is really important or we can discard that. So the upset theory is a classifier which not only classifies from the features, it will not classify the features, it will also can identify that what are the features they are most important. So this is an added advantage for a classifier. So that's why we have used upset theory, because from the cross-wavelength spectrum we did not have any idea that what kind of a thing we can, what kind of a feature we can choose. So there are different steps. I am not going into detail of those steps of upset theory. The point is it can classify, and how it classifies is that it actually generates various if-then-else rule, and from that it can classify. So the data table, whatever we get from your data, from feature extraction, so initially having the data, then the cross-wavelet transform, then from that cross-wavelet spectra we are getting some features. So the table looks like this. So A1 to A7 are those features, and this decision attribute is nothing but the class. So here you are having the four classes. So four different classes will be there, and we are having some data we have recorded. From that, we are trying to find out a rule base which will tell us that if we give some unknown waveform, what is the class, what is the fault class. So that Rupset theory actually classifies in that way. Initially, it is the real valued table, then it actually discretizes the table, and then it finds some if-then-else rule. The mathematics behind the Rupset theory is not the theme of this. That's why I am skipping that mathematics of the Rupset theory. If you are interested, I am having ample material for that. For easily understanding this, I can share it later on. But the point is, if we are using the Rupset theory, finally, what is the output? Output will be some if-then rule. That means like this. Here it actually indicates that if, say, A1, feature A1 is equal to 1, and your feature A3 equal to 0, if and A7 is 3, then your defect of type is, say, T1, like that. In this way, you can generate so many rule base, and it is another advantage of Rupset theory. It gives you a very simple rule base so that you can implement that in a very low cost microcontroller or low resource computational framework. So that is why it is very easy to implement once you get the rule base. And I'm talking about the point that why you should choose the thing that is cross-wavelet transform. Having one added advantage from this result, we can see that we are classifying with so many number of data, and many data are having noisy. We don't have to denoise the data, and this kind of data, if it is noisy, then also the cross-wavelet transform gives you a feature that is quite helpful and gives us a particular advantageous result. That means acceptable result, like 87%. With denoised data, obviously denoised data is always preferred. So the performance is 91%, but 87% is no bad. So therefore, the cross-wavelet transform is having an inherent ability to reduce the effect of noise because of that correlation sort of a thing. Because the noise are most of the cases uncorrelated. So therefore, the effect of noise in the cross spectrum features, they are not that much of visible. So that is the one reason we have chosen that cross-wavelet transform. Maybe in your problem, if you are trying to solve or use any signal processing tool, maybe some tool you have to use that will be having some added advantage for your problem in hand. So you have some publication. If you want to more detail, you have got the patent as well as one publication for that. If you search that with this name, you can find more detailing on that. Now, so the classical way of doing thing is that initially the feature extraction and classification, they are two different things. That means they are clearly identified as two different functional parts. One is feature extraction, and then we have to use those features in classifier. But in many cases, whenever your say classes are much more, not only these 4 classes that we have shown in the last case, if your class is much more, then or the thing is your system is much more complex. The rule base will be so complex that it is very difficult for you to find out what kind of feature you are trying to learn. Maybe those 7-8 features won't be enough. Maybe there can be a very hundred thousands of features they should learn, or maybe those features we cannot explain with a say closed form mathematical solution. So therefore, nowadays what happens for more complex problem, learning features earlier, that A1 to A7, those feature with mathematical equations, technically we call them handcrafted features. That means those equations are handcrafted, means we know the what kind of a feature, what kind of mathematical equation I am operating on the particular data, and whatever we are getting. Now maybe for some complex problem like this one, we do not have an idea that what kind of a feature it should learn. Maybe the feature is so complex that you cannot explain that in simple mathematical term prior to getting that. So here one problem I'm just showing, this is a box, and this box is having, say, you can say, I think this box is a transformer, a model transformer. So electrical transformer is there, and in transformer within the box anywhere there can be a partial discharge. So the locations are much more complex. So in this, within this box anywhere the partial discharge may occur, and partial discharge will throw you some signal. It can be electromagnetic, it can be acoustic, ultrasound. So the red dots, they are the sensors. Here I am showing you the acoustic sensors. They can be fitted on the walls of the transformer. Those red dots will capture some signal. And from those signals, you have to find out what is the location of the partial discharge. And as the location can be so many, so my problem is now a little bit of complex one. So this is the particular setup. There will be a high voltage transformer that will be giving you the required voltage to generate partial discharge. And this tank, this white box, is basically that sample box that is actually mimicking the transformer. And on the side, we can have the acoustic signal cable. It will record the acoustic signal. And after recording, it gives different kinds of signal like this. So those signals, from these signals, we have to identify what is the location. Because for one particular location, we are having 5 signals because we have used 5 sensors. So 5 sensors we can think about that it is like a say a projection. That means we are actually seeing the whole thing from different angles, like the top view, front view, side view of an image. So that from this top view, side view, front view, we can draw the 3D image. Like that, we are trying. We have recorded these signals using the acoustic sensors from different angles, and we are trying to find out what is the 3D location of the partial discharge or source of the signal. That is the problem in hand. So it is very difficult for us to know what kind of feature we should use. So here we have used nowadays this deep learning and machine learning convolution neural networks are very common. Maybe many of you are familiar with that. But those who are not, I am just giving a very brief overview of that. Say a network structure is like that. If you can think about a network, say a CNN as a black box. Black box with having so many layers. Layers are nothing but some mathematical operators. And in convolution neural network, initial layers do some convolution operation, then some other operations, maximum pooling, etc. Okay, more or less we are concentrating on the convolution operation. And then and the later portions, they actually do some sort of say classical artificial neural network sort of thing. We call them a fully connected layer, and they are called some classifier. So basically, the convolution neural network or deep learning network, what we are using here is that as a black box. And that black box, initial portion of that black box, they are doing some mathematical operation called convolution. and the convolution layers are actually the feature extractor. But what convolution layers are learning that we are not having any control over, but because those cannot be represented explicitly by that kind of closed form mathematical equation. So, in a nutshell, we can say that a convolution neural network, a black box, initial portion or initial layers, they are the feature extractor, and the later portion, they are the classifier. So now what happens is that our machine learning tools, we can use our signal processing knowledge in such a way that we can do feature extraction as well as classification with the same tool. We don't require two different tools like earlier case. That means for feature extraction we use cross-wavelet transform. Like the second case, like use for the classifier we use the rough set theory. Those kind of two different things are not required here. So what we have done here is that those convolution layers we use that wavelet function as the initial kernels. That means that it is a black box. We don't have the explicit control that what it is learning. But what we have done is that we know that wavelet based features are quite good for partial discharge identification from our earlier knowledge. So that signal processing knowledge we have used that those convolution filters we use as they will be used as a mother wavelet. That means those convolution actually they are actually randomly initialized for classical CNN. What we have done is that they are initialized with mother wavelets like this. Like this. These are the waveforms, these are the kernels. So these waveforms will be convolved with the signal and some features will be learned. And this is the thing. Say some Morlet, Mexican and Mayer, these are the Daveshi, these are the name of various mother wavelets. And after different iteration, those mother wavelet will get changed because they will be updated. And finally, what we'll get is not exactly a mother wavelet, but still it will be having some nature of wavelet so that whatever we are learning, it is something related to wavelet features like that. So now we have designed one complete network that is synergism of two different things. One is signal processing tool that is wavelet based feature extraction, and also the classifier that is a neural network classifier sort of thing. And they are merged together so that we cannot segregate them, that this part is explicitly feature extracted, those part is explicitly classifier. Not that. It is not the separate thing. It is only one common network. Initial portion, they are actually extracting the features, and later portions, they are actually just classifying those features. But there is no sharp division that, okay, up to this, it is the feature learner, and these features are deliberately learned. It is not like that. So there is no question of any handcrafted features. And this is a confusion matrix, and this confusion matrix shows that we have got a very good classification result in that case. So if you are trying to find out more detail, this is the source. This is the paper, our paper. It is published in a high impact factor journal, and you can find this. So more detail you can find out how you have designed, what are the parameters you have chosen, like that. Another one is that this condition metering of overlaid line insulator, because you know that there are so many insulator and manual checking of each insulator is not possible. So if we can have one, say, sort of that checking by maybe there can be a signal that is being recorded on site and we can process it locally, then that can be and sending the signal, then we can have this kind of an automated setup which will just avoid that manual intervention for each and every insulation condition. Because insulator, this overhead insulator, if they are very much aged or very much polluted, so that surface leakage current becomes high, so there can be a dead short circuit. So this is a laboratory setup. It is not very important for our discussion. But the point is, we have taken, say, 5 classes, and those 5 classes you are trying to classify. So 1, 2, 3, 4, 5. These are the 5 classes. One is very low, low, moderate, high, and very high contamination. That means if it is very high, then we have to check that particular insulator and we have to replace, we have to do something with that particular insulator. If it is high, then also the same high alert will be there. Moderate means it is a low, threat for that. And low and very low, they are more or less safe insulators like that. So the signals that the surface leakage current we record, these are the surface leakage currents. That means from a very smooth sinusoid, whenever the contamination occurs, there will be some harmonics present in that. So if we are trying to find out very accurate identification of the progression, whether it is in between class 2 and class 3, class 4 and class 5, like that. Because see, the point is, you can say that, okay, by manual inspection, we can see what is the utility of using any AIML tool. But the point is here, say class number 5 is the class number 4, they are the vulnerable class. Class number 3, they are the vulnerable classes, because 3 is moderate, then it is class 4, it is high, class 5 very high. The last 3 waveforms, you can see more or less they are having similar sort of nature, but one is more dangerous than other. So how from 3 to 4 and 5 this gradual progression is occurring? If we can identify that, then only we can predict the condition properly. Maybe it is now at class 3, maybe it is having progressed up to class 4. So what is the actual condition, whether it is how much it is on class 3, how much it is belonging to class 4, this kind of a thing we should identify. That is why that is not possible in by manual inspection. Manual inspection, you can have coarse classification, but the finer classification you should use some signal processing tool. And for that, we have used here one, it is called the multi-synchro squeezing transform. I am not, this is a mathematics, okay, forget about the mathematics. The basic idea is that I told you that wavelet transform gives you the time frequency localization. Now the point is, for wavelet transform, say this left waveform is having some change in frequency, and change in frequency is just this yellow line of this wavelet transform is having those frequency, but you can see that actual frequency is the black dot, but actually what we get from the wavelet transform is this green and yellow region. It is technically called frequency smearing. Smearing means the frequency localization becomes a bit of hazy. It becomes hazy because those who are very good at say Fourier transform and other things, they can understand that if you are using one wavelet function that is having some frequency and time localization, frequency bandwidth and others. So within that frequency bandwidth, what is happening, those frequency we cannot identify properly. Technically it is called, in signal processing it is called uncertainty principle of signal processing. So therefore even though you are using signal process wavelet transform in signal processing, those black dots are the exact frequency, but wavelet transform will give you sort of a bandwidth of the frequency. Exact frequency pinpointing may not be possible. So multi-synchro squeezing transform is, it actually gives you that idea that it actually squeeze. That means it actually squeeze this kind of an waveform, that is, say this yellow, if we plot that in 2D, it looks like this bell-shaped waveform. So if we squeeze it and find out what is the peak, we can get this dotted line. So multi-synchro squeezing transform does, what it does is that it actually squeezes those frequency smeared regions, and it actually concentrates those frequencies so that we can minutely find out what are the frequency components. And we can find out from these waveforms, this kind of an waveform. Here you can see very fine lines are there. I am not sure whether they are clearly visible or not, but those fine lines indicates those actually time frequency localization much more better than wavelet transform. So now if we can just use this kind of a frequency localization, then we can find out what is the actual condition of that insulation, so or the overhead insulator. So in this way, you can use this. The same CNN model you can use, and that CNN model will learn those spectrums. Earlier, we have given the input to the CNN module that cross wavelet spectrum. Now we have given this kind of a multisynchronous spectrum. As the time frequency localization is more finer, that means the resolution, frequency resolution is better, so the result will be better in this case as it is expected. So this is a sort of error representation. Those who work in various machine learning application, they know how to represent the error. It is not about only the accuracy. It is also accuracy, then sensitivity, specificity. This kind of a thing are also important. So this is a typical structure. Those who are very new to this kind of a representation work, they can just take a look of this particular thing. All of the performance indices, they are mentioned here. And the performance indices that we got were very good. That's why I'm representing. Otherwise, there is no point representing that. So here we have used another advanced signal processing tool with the classical, say, CNN, classical convolution neural network. Then we can have a very good result. Similarly, have applied that in case of skin diseases as well. Skin disease could be of various types. In India, say skin cancer are not that very much of very important, because here other than skin cancer, the other skin diseases are very important, like say psoriasis, tinea, like this kind of a skin diseases are important. Now the point is, the skin diseases in many cases they look similar. That means it can be the medication will be different, but apparently looking into the skin patches, it seemed that they are almost the same kind of a disease. So if we can just have some second thought or some algorithm is there that will help the dermatologist. Dermatologist means we will process those images, and if we can have a second opinion from that this kind of a machine learning tool, maybe some hidden information from those images can be extracted. And that we have done using some fractal features. Say this is one, say patch of a skin portion, and you have to identify whether this is having some disease or not. It can be all the data we have used here for skin cancer detection. So whether what are the things, usually we talked with the dermatologist, the doctors we discussed, and they told us that they actually just find out what is the irregularity of the border. That means if there is a skin mole or something, skin patch or skin lesion is there, what is the nature of the border? More regular border is less harmful. Very irregular borders are harmful. And different pigmentation or different color changes within that particular patch, that is also the thing to look into to identify the disease. So whatever we have done is that we looked into all the things in various ways, and we applied this kind of the basic idea of the CNN structure. It is not a CNN that we have used. It is the idea of the CNN. So many different convolution layers. Here we have used as the image kernels as the convolution layers. So various standard image kernel with known cases. We have checked all those known cases from the dermatologist, and those known cases are stored, and unknown image will be compared or convolved with all those known cases, and the features will be classified. So these are the features. Those high regions gives you the similarity for various cases, similarity and dissimilarities. Red regions means high similarity, blue region means the less similarity. So according to that, those regions we have identified that what is the disease. Another way of identifying this is that the superpixel. Probably many of you heard the term superpixel. At least the pixel is very known to you, because nowadays the common mobile phones and etc. we always prefer high megapixel cameras. And superpixel is that the region, various regions of similar kind of pixel nature, they are classified as the same one. For example, the left one is say a skin lesion. The middle one is some image processing application. We call it segmentation. So some regions having different patch property or color property or texture property, they are actually with different colors. Now we apply some algorithm that is actually classifying or that is actually grouping similar network or similar pixel regions. So that is called the superpixel. So now if we get the superpixel and each region wise classification if we do, and we can have the better result or performance. Now the point is up to this is fine. So let us have a brief recap of that what I have told. I told that initial synergism of signal processing and classification was quite vivid. That means we can segregate the classifier with the feature extractor. Feature extractor most of the cases the handcrafted features. The classifier is a signal processing tool. Then we have used say a classifier that can be say a rough set theory or any ANN or CNN or any classifier, support vector machine, etc. Later on, synergism become more complex. That means no such segregation is possible between the feature extractor and the classifier network. So it is sort of a black box. We give input and some part of the network learns features, some part of the network actually classifies those features like that. Now it is very difficult that to believe a black box. Maybe what if we can explain what this black box is learning, then we can make the learning better. So this kind of a thing is nowadays is called that explainable AI. That means explainability to that particular artificial or machine learning tool. So we have tried that as well. That means this is a skill lesson. This is a common CNN structure. It learns and gives some accuracy. Then we found out which region of this image gives you the particular classification result. That means what is the importance of the region of that particular image that actually gives you that particular class. For example, say this is the image. It is say a malignancy, a skin malignancy. Say it is a melanoma. So if it is a melanoma, then the classification that it can be say class 1 say melanoma. So it is classified as class 1. So what are the regions of this image? What is the importance of this image? That is actually giving you that particular melanoma classification that we are trying to find out. Here the image, red colored image means those regions of that particular image is having more importance in decision making. And we have shown those regions to the dermatologist and they actually corroborated, okay, there's some region. That means now we can say that, okay, my black box is learning something which is having some physical meaning. Otherwise, it may be giving you, say, some result which can be totally, say sort of an, out of the chance it is giving you the actual result, but maybe your actual learning thing is something else. So therefore, in this in image, you can find out those red regions are actually marked by the dermatologist. Those regions they are actually given more importance. Similarly, what we have found out here, it is not the those regions. Here only the pixel color actually shows the importance. More red means more important in decision making. Those regions. So in that way, we can have this kind of image processing concept or image processing understanding in case of your learning understanding. That means we can explain what it is learned for a particular black box sort of network. In this way, we can do so many things. I should stop here because there can be so many questions on that. Even if it is not, then no problem because we can ask later on. We can discuss later on as well. So this is my. I should acknowledge my scholars. Nowadays, all my scholars do the work. We actually present their work and take the credit. So I must thank my team. Many of them have already got that PhD doctorate. So one name that is Mr. Amitabu Alda or Amitabu have already got the PhD. So and these are some references. it is said usually that if you copy from one source, it is plagiarism, and if you copy judiciously from several sources, it is a classic work. So I have copied different things from different sources, some of our own works, and I have presented my lecture on the basis of these two books and some works of my scholars. So these two books you can check if you are interested in further details. So thank you for patient hearing. If you have any questions, please ask.
Thank you, sir, for your informative speech. Now, I would like to request all the participants, if you have any queries, please ask.
Sir, my voice is audible.
Yes, audible.
Yes, sir. Sir, you have told about CNN network. Can you throw some light about the difference between ANN network and CNN network? Excuse me, sir. Sir, your voice is not audible, sir. Yes, sir. Hello? Hello? Yeah.
Sir, your voice is not audible.
Sir, actually, your microphone is off.
Oh, sorry. I have switched off my microphone. Okay, yes. Sorry, I have switched on the video. So that's let's stop that again. So the thing is, what I'm talking about? Okay, your ANN. It is sort of a basic building block is a sort of perceptron. It is called. So the simply speaking, say there you are having data x1, x2, x3, x4 like this. So x1 will be multiplied by some weight factor w1, x2 will be w2, etc. And those multiplied thing they will be summed up and will be subtracted and will go through some another function like that, and there will be some output. For CNN, that is deep learning, here there will be so many layers, and those layers, it is not only there's some multiplied by weights, but in a different architecture, so that you can represent that like a convolution function. That is, there will be some mathematical equation, and that or some you can say a matrix or array. Those matrix will be convolved with another matrix. So that is how it learns. So it is a sort of a unit building block is same, but as a whole it is much more complex. So that means it learns much more things. I do not have a representative very basic diagram for that CNN. Then otherwise it will be very. But online you just search that there are so many resources nowadays available, very lucidly explained using images. That what is a basic perception model, and then how we can move on to say CNN model.
Another question, that is, sir, nowadays new technology has come, that is cell technology. Cell technology, lot of machine learning algorithms are coming nowadays. It's a novel thing. Nowadays in America it is going on. So, sir, can you throw some light about cell technology algorithm? It's a completely new algorithm, novel algorithm is coming. Global optimization algorithm, actually. Cell
Yes.
technology, sir.
Yes, global optimization algorithm we can always have. Because it can be evolutionary sort of algorithm or the swarm intelligence based algorithm. There you can have so many initial guess or initial solutions, then it will try to all over the spread all over the search space, then it will try to converge according to some algorithm. There you can think of say PSO, you can think of that means particle swarm, you can think of say differential evolution, and so many other global optimization techniques. You can apply them as well during learning.
Okay, thank you, sir.
My work is mostly related on signal processing, and as a part, as a tool, we use the machine learning tool, because most of the cases we give importance on the signal processing, how to embed those signal processing tool in that particular machine learning algorithm.
Okay, sir.
Anyone? Okay, if not, then
Okay. Okay, now I would like to request our HOD Chair, Dr. Suman Kumar Dey, to give vote of thanks.
Thank you, Arpadi. First of all, I would like to give my sincere gratitude to Debangshu sir for his valuable speech. It will definitely helpful for our students. Thank you, sir, very much. I would also like to give my sincere gratitude to Mr. Shonpal, HOD EE, Mr. Minmoy Dash, Assistant Professor EE, and Mr. Arpadip Mondol, Assistant Professor EEE. Last but not the least, I would also like to give my sincere gratitude and thanks to all the faculties and all the students present over here. Again, sir, thank you very much. And now I would like to give a small token of appreciation virtually, and I would
Thank
like
you.
to request you to accept it.
Yes, sure. Thank you. It is very nicely designed. Thank you. Thank you. Thank you
Thank
for
you very much.
inviting me. Thank you.
Thank you, sir.
Thank you, sir. Now I would like to request all the participants, please fill up the two feedback form. One is for the previous seminar and another one is for the present seminar, which was shared in the chat box. Please fill those feedback forms.